Good afternoon, guys. All right, so what we're going to talk about today is some more details around this concept we brought up last time. These are the Meyer reactivity scales. So this is a bridge over sort of what you consider as modern linear free energy relationship examples. And the one I brought up last time was just this open concept. So Meyer did a couple different things. The main one was sort of the concept of bringing up a chemical reactive sequence where he defined electrophiles that had particular reactivities within a certain scope of nucleophiles. One of the problems he realized, though, is, for example, with this specific example, that was the reference electrophile he was focusing on. The reason that that was good was it's a clean reaction. It's just a nucleophilic capture of a carbocation. This is a long-lived carbocation, and it happens to be colored. So basically, it met all the criteria of both being a colorimetric probe, having good reactivity, other components. And then the nucleophilic addition of that one gives you this colorless material, which just gave you a very accurate and easy way to measure your Ks. The challenge they ran into, though, is if you look down here, this is the corresponding sequence of nucleophiles, and he was focusing primarily on either pi nucleophiles originally. So these are double bond or pi nucleophiles capturing this carbocation. And what they found is for any individual electrophile, there was a range of nucleophiles where you could get sort of useful data. So in this pairing, these were the slow ones down here, but you could still get measurable rate constants on a decent order of time. To these are the more nucleophilic ones, so they're faster. Anything like these ones, the sort of true enolates or the silyl enolate systems or enamines or these other sort of nitrogen nucleophiles, these guys are way too fast for this specific electrophile. Same thing on the other side. These ones are way too slow for this specific electrophile. So the need was to expand out other structures that would allow you to quantify molecules like this or molecules like this, which just means tamping down a partner to find either more reactive electrophiles to access this end of the spectra and less reactive electrophiles on this end of the spectra with those similar concepts. So where all this came back, though, was in this starts in the 1920s with Lewis' valence bond theory. So this is the whole idea that, first of all, if we're going to do nucleophilic capture, we're going to focus on molecules that are be dealing with the valence electrons is where that reaction is going to happen. That branches over to nucleophile-electrophile chemistry and coupling, and then eventually up into what was quantification. So all the stuff that Herbert Meyer was doing started back where there was just an assessment of reactivity pairing. All that's really happening there is this is exactly like what you saw for things like KSP and pKa type values. So the concept is if I take a reference nucleophile, in this case maybe water, and I try to measure how fast a reaction is with, in this case, an SN2, simple alkyl bromide, what I'm going to get is some kind of an equation where I'm measuring how fast a reaction is by measuring the ratio of the two K values for that particular coupling. So just like pKa, it's like an acidity scale is basically referencing a single component. This is acid-base in the presence of water. None of these slides are online. You don't have to find them at that point. I did not put them up. Okay. So the goal here, right, is that you have a reference nucleophile, that's your Kw on your bottom, and then what you're doing is you're saying for any other nucleophile, relative to water as my standard, how does this actually going to rank in terms of faster or slower? But it's still that same idea. This part here, a log of two rate constants, that's the same thing that we saw with the Hammett parameters. It's just measuring out some 2 points. You use a ratiometric measurement on whatever your setup is, and then you're using that as a way of coming up with a numerical scale for this part. But this is, again, this is just classic where this idea kind of came up. What they started doing was this. So the graphs that you get out of this kind of field look like this, where you're assigning some value, a nucleophilic constant. So in reference to something like the Hammett parameters, think of this as like your sigma value. So what it is it's the value n that they came up with. They just defined this value n for some electrophile is just the ratio of rate constants against a reference nucleophile. So if the nucleophilic parameter, or they define this n value here for water equal to 1. So you're basically saying for water versus water, it's a ratio of log of 1. We're calling that value of n equals to 0, and that's just putting this on the reference state against this. Then as we go through, and then for different electrophiles, we're changing the nucleophile. We're doing this pairing. So following along here, if this here, that's our water. So water is our statement across this. This line corresponds to how does whatever that reference electrophile is as I'm changing different nucleophiles. So this bottom line here is, let's say I start with this cationic electrophile. That's the K value for that one pairing, that electrophile against water. And then what I'm doing is I'm going to different nucleophiles. So in case up to here, this is hydroxide. So if I go to a hydroxide system, that data point there is how does hydroxide react as a K value with that electrophile. And the first thing that they found with this was that they thought was really surprising. For certain electrophile pairings, as I walk through, remember, as I'm moving along this axis, I'm trying different nucleophiles. But as I walk up this line here, what I'm saying is that for some constant electrophile, as I move through different nucleophiles, I'm getting something with a defined slope. Okay, so great. That means I've got this predictive line here, which might give me some predictive value. Then what I'm doing is, for the same nucleophile, but a different electrophile, you define another line. And then same point, same nucleophile, in this case water, different electrophile, and you're just going through that sequence where you're just changing one by one these permutations. The weird thing that jumped out of this is you had a whole bunch of parallel lines. So what that says is, yes, if I take a very hot nucleophile and a very hot electrophile, I'm going to get a very big K. Fine, that's just, it's fast. The thing that they found striking, though, is these parallel lines are kind of like saying it doesn't really matter what the innate nucleophilicity or electrophilicity is. All we're doing is we're watching reactions on a faster turnaround. What they were charging against this was a philosophy as anything that's a fast reaction innately is going to have worse selectivity. So basically, we can't even if I have two things, it's a really hot electrophile and a really hot nucleophile, things will just go nuts. We're expecting a much higher order sort of response. But in fact, what they were seeing here is these very predictable behaviors where if you said, if I have a certain electrophile that was along this line here, and I said that mixture has one nucleophile and a second nucleophile, that right there is a fixed amount or fixed relative ratio of selectivity. So given any individual electrophile and two different nucleophiles, this graph would tell me that the ratio that I'm ever going to get is constant no matter which parameter it is. So basically the innate nucleophilicity or the innate electrophilicity defines what the selectivity is going to be, or as long as you're dealing with a kinetic step, right? You're basically saying that the reactivity between two parameters based on how big the relative K values between the two is defined through a very large degree of reactivity. So the original ones were all done initially using sort of simple cationic couplings. Then it was jumped over to organometallics. So this was the work that was being done primarily by this group. This ChemRev article talks about how they started to extend it over to broader compounds, and these are things like organometallics for Grignard reagents and things like that too. So once again, you see these kind of pairing where what we're saying is in a simple binary step, you get this sort of constant behavior. And again, the interesting thing about this was it allowed a way to fingerprint reactions that were sort of single transition states. Well-behaved systems had these kinds of pairings across a very wide degree of point. But this constant selectivity relationship was a really interesting philosophy because it meant that you could do measurements on the relative selectivity here and predict what your relative selectivity would be on a completely different end of the spectra. It was baked into the different electrophiles. This is just a simple way of saying that they were trying to prove that models that they could run on one kind of a series of reactions probably could extend to chemistry they hadn't run yet. So this is, again, this idea of extrapolation. Herbert Meyer picked up at this point, and his whole thing was, again, looking across a wide variety. The comment here was, in the case of the organometallics, this is over 9 orders of magnitude of the overall rate, and you're still seeing these kind of parallel lines showing up. The original work done with just the simple diazonium type ions and stuff like that were usually over smaller ranges. What Herbert Meyer picked up was he thought this was really interesting. There's these large ranges of reactivity, but this still is only representing a very finite number of possible reactions. Like there's a much wider range of overall reactivity that's available. So what Meyer wanted to do is say, all right, let's go to those really far extremes, the very, very slow reactions versus the diazonium to the exceedingly fast ones that we can't see right now. Is there ways of coupling together this philosophy and actually building a universal scale that actually went over a much larger sort of point? That's in the paper I showed you last time, everything that might be sort of rate constants on the order of the Big Bang all the way down to something that's on the nanosecond or the beat of somebody's wing. That was just kind of his driver. So what he did is he said, all right, the original nucleophilicity scales we had was this. We're taking the log of two rate constants. Remember, the reference is water here at the bottom, and that's what we call their nucleophilicity parameter. Well, we can do, if we separate this out and derive it like this, all we're doing is we're just breaking out those two equations. What that does is it isolates this value here, and we're going to call that the electrophilicity. So now what we have is a single K value I can measure for some property, where I'm measuring this K value for any electrophile-nucleophile pair. And if we went through this, we could actually assign these E values to any electrophile, N values to any nucleophile. If I knew what those reference values were, I could probably predict what the resultant K is for that sort of AB pairing across any space. So the goal of this was kind of the expansion of the Hammett parameters. If you were to measure E for a whole series of different molecules and N for a whole other series of different molecules, you'd have a reasonable idea of what the rate would be by mixing those two together, even if you never ran that reaction yet. That was kind of the hope. So he started off with these reference compounds, the ones I showed you at the beginning. Again, why? Because these were colored, they were easy to pull K values, they were well behaved, so that was just where he defined his kind of zero space. So he just defined this as E equals 0 for this component. And then simple nucleophiles on this one were mainly based on the sort of pi philic systems. Again, these were just a decision started out. The one thing he did add to his equation was this. It's what he called the slope-specific parameter. Up until now, the ones I've shown you, these are all parallel diagonal lines. And what we're saying there is that, okay, the same reaction persists, or the selectivity of one nucleophile pairing persists over the entire sort of experimental range. The problem is, as you start to get to other transition states associated with different nucleophiles, this goes back to the thing we talked about with that sort of three-dimensional surface. There's some nucleophile-electrophile pairing that have either more early or more late transition states. So these are geometric things where, let's say, for some nucleophile, sterics matters a lot more than just electronics. And what you'll get are these nonlinear behaviors. And as a result of that, you get different slopes. So what you get is in a well-behaved system, looks like this. This is what we're saying is that across the entire electrophilicity scale across that with this reference nucleophiles, these kind of pi philic nucleophiles. Here what we have is all the nucleophiles being tried. That's our diagonal line. All of these individual lines here, these are different electrophiles. And it turns out that for that specific pairing of these simple terminal olefins, the electrophiles being tested gives you nice parallel lines across it, which means the selectivity principle we saw before is being held. Everybody is the same, that I can measure relative selectivity at this end of the scale and predict what the selectivity would be over on this end of the scale. What happens, though, is if you go to these guys, these is an example of different nucleophiles. Here you have one where there's a diagonal element that's kind of cross-cutting. So that's a case where for whatever reason, that specific substrate has another factor which is non-linear to the other one. So this is where the S value that you would have has to come back in to bring everybody back into line. So instead of just saying that electrophilicity times nucleophilicity will give you any prediction, now you've got this S, or this slope, that would allow you to sort of still use this across a predictive range. And again, I'm not going to go into some of the details about why you get this curvature, but functionally what it comes down to, you'll see probably, is some substrates you're also breaking, let's say, aromaticity as you're doing the nucleophilic substitution. So there's a bigger push and pull associated with it. Or some substrates are very, very sterically encumbered, let's say, and then they're going to have different impacts as you go over that series. But suffice to say, usually what would happen is just the slope would help to correct it. Yeah? No.
You're talking about selectivity, and I think maybe my brain's just lagging, but
Yeah. What I mean is, so if you look at, let's say, these four here, what we're doing here, if I stay on this column, all of these ones in this column are using the same electrophile. So I've chosen one electrophile, and what I'm measuring there is for this top one, I'm using that nucleophile, let's say. This next one down, this is my nucleophile. So what I'm doing is I'm saying 1, 2, 3, 4 different nucleophiles, and I'm comparing how fast does those four nucleophiles individually react with the same electrophile. What I mean by selectivity is, if I was to run these on their own, I could say, remember, this value here is much faster than that one down there, right? It's a higher K value than the other one, okay? What it means is if I put both nucleophiles in the pot at the same time with the same electrophile, now it's a head-to-head competition. So the selectivity there, assuming it's just one step and there's only one K, it's under kinetic control. So what I would assume is if this one, for example, was 4 times as fast as this one times, at equal concentrations of those two nucleophiles, I would predict that I'll have 4 times the faster product as the slower product. That's what I mean. Does that make sense? So again, the big hand-waving part here, we're saying it was termed as selectivity because we're assuming we're under completely kinetic control. We're assuming it's just a single transition state, and it literally is a foot race between 2 different nucleophiles against the same electrophile, or reciprocally, 2 different electrophiles against the same nucleophile. So in the end, the K values and the ratios of the K values of here would predict product distributions, is what comes out as. That's why that point. Cool? So, the part that got fun, and just as the reason why Herbert Meyer is like a personal hero in this point is he started doing all this work right at the time where being a physical organic chemist was a dirty word. And for anybody who knows what happened with things like, there was a crisis in the field called the non-classical carbocation disaster. Does anybody know what the non-classical carbocation is? Yeah, you know, the Norbornene thing. Basically, the best way to summarize it is too many people started arguing about the underlying shape, quantum mechanic principle of the non-classical carbocation, that billions of dollars of research money went into this, what seemed like a pedantic, you know, angels on a pinhead discussion that had really no tangible benefit, and everybody got very, very pissed off, and then basically all the funding got pulled back. It was sort of, they went through a cycle of people, you know, federal government showed up and said, why are you spending federal dollars, you know, studying how painting cows black is a good thing or something like that. It was very bad for the field. My point is, Herbert Meyer really loved this idea. This was a whole legacy of love for his entire career. He somehow focused on just doing these kinds of very careful, first of all, think about it. You've got to come with exceptionally careful synthesis to build these kinds of molecules and handle them. Then once you've got those molecules, they need to be pure. Then you need to build all the other technology to actually do the measurement. Then you need to actually do all the measurement across every system. And he's creating these massive sort of reactivity scales. All the numbers that came out of this is what sort of fueled most of what is modern computational chemistry and ML, because these were the foundational data that helped to train all those sorts of things. Yeah?
So speaking of the technology piece, do you know how they track this stuff?
This was primarily photochemical, right? So he built systems that the electrophiles were colored, and he's watching disappearance of color over time. Like that's partly what they did is they had simple spectroscopic optical methods to watch starting material to product where color was directly correlated to concentration. That's why this made it possible. Sometimes literally colorimetric, like literally these ones, I've got some slides later on, but some of these are just, they're blue, they're red, right? So they're actually in the visible. But yeah, these are stop flow type measurements where you're watching rapid disappearance of color and you're just using simple photochemical and UV type measurements, yeah. Again, so that was his legacy. This is one of his examples over a huge range of these particular electrophiles, and then correspondingly across all the other nucleophiles. In the end, I think where we landed up was, again, some of the stats, 38 different pi nucleophiles, 23 different carbenium ones is where they kind of started out, but since then it's expanded huge across a wide variety of space. So if it is something that you're ever building, if your job, if your interest does kind of go to this thing, if you want to sort of level set possible reaction parameters, what catalyst might catalyze what kind of reaction, a lot of the primary physical data can be found on some of these kinds of the graphs and stuff that he built out. Originally it was all the pi nucleophiles, but like I said, they extended it over to things like hard anions, enolates, iminiums. Most of what we now know for like selectivity principles for things like organocatalysis and ligand behaviors all come from these kind of these points. If you've ever heard something that says, you know, this is why we assign a primary amine as more nucleophilic or less nucleophilic than like a hydrazine or a hydroxylamine, it all comes from these kind of original sort of examples. And then again, these are mainly just for your reference in terms of the broad sense of different sort of pairings they have. The one that where was it? This one. So his legacy basically comes down to this website. It's well over a couple thousand, over 900 nucleophiles and 200 electrophiles is what I pulled up yesterday. And again, you have every cross pairing of those ones actually sort of validated data. So this was a lifetime of sort of work to kind of put in. It's all free, it's all for, open accessible, and in fact, again, this was just something that, the interesting story, if you dig into it, is that there was a bunch of periods of time where he was completely defunded and sort of found money in different places to keep this work going over the years. And now that this data bank is sort of in place, it's something that is kept up by the community. But literally, he was building all this stuff with this foundational data that was only until the last couple years where direct reactivity training models really mattered that suddenly this all sort of became like absolute gold, right? It turned out that I think Tsinghua University was the one that backed them up on this point, which means they own all of this stuff, and the IP is unbelievable. But this is one of those cases of, again, they bought a lottery ticket at the right time. The really important thing I want to focus on, though, is, okay, so the scale exists. Let's say you have a new nucleophile or a new electrophile. How do you go about building a new E or N value? So the way you would do it is one of two different ways. Let's say we have a new electrophile. How are we going to assign that electrophile a new E value? So what we would do, so remember, on the scales that he provides, usually he's drawing it where nucleophiles are on the diagonal axis, so different nucleophiles are sort of your diagonal component, and the electrophile is across this scale here. If you go back to his equation, where was it? This is the Meyer equation. What we're saying is, I will measure the K for some nucleophile-electrophile coupling. I have an assigned, these are your parameter values for the nucleophile and electrophile that you're putting in that reaction. Your slope is the value that you have to know for whatever that series is. And again, the slope would be something where for some individual, remember, because the diagonal is your nucleophile, the slope would be corresponding to some nucleophile across some electrophile series. So because of that, first thing I can do on my scale is if I can get to a place where nucleophile equals, or the value at this, where this crossing is here, where log k here equals 0. So that's a case where you're saying that, remember this is a ratiometric measurement, k over k. If log is at that point right there, where log equals 0, that's the point where your electrophile, or the minus E value, is equal to your N value. So that's just a mathematical extrapolation. So what that means is, if I assume that there's a linear relationship, if I measure 1, 2, 3, these are your different electrophiles, for some nucleophile, I can set up what looks like a straight line. I put it onto my chart where what I'm measuring is the K, the log K values for those three values. Once they're on this chart, and if I draw a straight line, I'm drawing it down to that y-intercept. Wherever that y-intercept value is becomes my new N value for this nucleophile that I'm actually testing. So I have a new nucleophile that I'm interested in. I will rank it against 3 known electrophiles. If I know those 3 electrophiles, I'm going to come up with a slope. I'm going to put it on this part where I'm measuring the K value for those 3 different electrophiles, and then I'm going to extract or extrapolate back to y equals 0, or the y equals 0 value. That minus E value assigns me the N for that my new nucleophile. Now the thing, when you do that, you're assuming that you have to do at least 3 values across this one and extrapolate back. The other way that you can do it, the sort of quick and dirty way, would be I have a single new nucleophile and I have a series where I've already measured and done this extrapolation back that is similar. So in this case, if I had this enamine and this enamine, what I could do is do that full computational study. So I'm doing 1, 2, 3 experiments and doing my extrapolation. What that does is now I know roughly what the slope value is, and I'm assuming that that's the slope for enamines, or iminiums in this, enamines in this sort of case. If I jump over to a new enamine, so it's structurally similar, I measure a single value. What I can do for this one is I'm assuming that the slope that I measured for this guy is probably the same for the slope I measured there. So a single value and then an assumed slope will allow you to do the same sort of extrapolation back to your y-axis, right? So there's two layers that you can do down. So this is kind of the sequence that he went through is if I already have a series of known electrophiles, I can now put any nucleophile on this while using at least 3 measurements and then an extrapolation. Or if it's structure related, I'm going to do 1 measurement and then use the slope from that other series to do that extrapolation. Your electrophile value is a similar point. You have to have a couple of known N and S values for whatever that nucleophile is, and you're going to rank it in that series against a different electrophile. So it was, his entire group was based on this point of like, okay, since we've got this whole set, we're going to slowly build out larger and larger sequences of molecules. You can see this from an experimental point of view. One of the more difficult parts, right, is if he's actually going through and doing ranking of molecules like this, a lot of the molecules he uses are actually quite unstable. You know, from a synthetic point of view, they had to solve problems like how do you make and isolate and handle only that enamine as an isolable material that's not going to hydrolyze on you or not going to break down, right? So this is where the real challenge with a lot of Herbert Meyer's work is not just, okay, these are the underlying values they went in, but if you actually go back and look at some of the ways that he went through and came up with making and isolating some of these things like very unstable tosyl imines or very unstable enamines. For anybody who's done organocatalytic work, these are all catalytic intermediates that are really, really, really hard to isolate. And in fact, there's some gems in his synthetic work that tells you about these very interesting tricks to both make, handle, and actually titrate these really, really, really reactive molecules that normally we don't have synthetic procedures to actually go through and do. So as a flag, if you are interested in sort of, you've got a reactive intermediate or you're trying to do a synthesis that is very difficult to isolate or handle, there's actually a ton of stuff in his work that can be inspirational. In particular, what I learned specifically about these enamines, you can take things like TMS chlorides and things like prolines and do some really, really interesting ways of stripping out water by making silyl water in this context, when it basically becomes these very, very energetic and very hydrolytically sensitive conditions for doing these isolations. So I do encourage you guys to kind of dig through some of the procedures for how they made some of these starting materials. Actually became even a bigger gem. Anyway, how we actually apply it. So once we've got the scales, what you can do with this, and this comes back to this concept of, back to the selectivity concept we talked at the beginning. The first step you can do is if you had a pretty good idea of what your E value is and what your nucleophile value, the first step he said is that, okay, look, for some species, if I'm expecting a 50% reaction conversion over about 3 hours, that means the K value that I needs to be on the order of about 10 to the minus 4. So that's just, you know, that's your normal rate constant point. If you're not going to be waiting on this for a ton of time and you're assuming a bimolecular reaction, then that's about the size of the rate constant you have to deal with in terms of orders of magnitude. Because of that, getting a reaction to run at a reasonable timeline at room temperature means your E and N values, E plus N, must be less than minus 1. That's just falling out from his equation. So if you've got that first point where you're saying, remember, log K is equal to S times N plus E, and I'm assuming that my K has to be in that sort of 10 to the minus 4 kind of magnitude, it means that that term, E plus N, must be in this kind of minus 5 kind of region for it to make sense. So this is where you could look at different materials and say, all right, that's my nucleophile. There's my E value. Here's my N. That E plus N for this combination is minus 1.14, which would give you a predicted K value, assuming S is equal to 1, of something about times 10 to the minus 2. Okay, that's reasonable. Now for this one, there's your N for a different material. E plus N for that one means there's going to be no reaction if you're trying to use that electrophile. So what I'm testing there is to say, given this electrophile with an E value of minus 8, and these two nucleophiles, nucleophile equals 6.8 versus 1.0, that combination is not predicted to do anything, or at least not fast enough, versus the other one, it would actually be productive. So first half is, this is just a quick spot check where even if you don't know in advance if a particular reaction will happen at a particular time point, you could go and do the lookup on the table, or just like your pKa values, find a structure that's on the table that has a similar N value, and then come up with an idea of what you think this N or E value would be. So this was okay, spot check. You don't have to do the reaction. You could look in advance and say, all right, for capturing that specific organometallic compound, which nucleophile am I going to need to do it on what particular time point? Great. The bigger application of this same one too is if you're going through and doing a catalytic, you're proposing a catalytic mechanism. So let's say this is a case where you're not starting with this specific organometallic, or maybe like we talked in the other ones, the enamines, these very reactive nucleophiles. You could start off with a catalytic system that might form molecules like this in your proposed structure. And then you're making, because of your statement, you're saying, oh, if this is my mechanism, I'm generating a molecule like the one I have in the top as my electrophile, and maybe I'm generating another molecule like this one as part of my co-catalytic system as my nucleophile, and I believe that this step, this coupling between the two of them, is very, very, very fast. Well, you could go back to the Meyer reactivity scales, find those two molecules and say, is that possibly true? Is it, if I were to generate these two materials as catalytic intermediates, is there possibly a fast or a slow reaction predicted from this one? So if you go back, for people playing in the sort of photocatalytic world, some of the early suggestions for rapid radical rebound capture basically start to fall apart in the same way, where the proposal was a particular reaction produces a particular intermediate like these reactive compounds, and in order for the mechanism to make sense, that reaction must be very fast. K must be times 10 to the 8. And the Meyer reactivity scale says that no, in fact, we've looked at that, and there's no way it's in an order of magnitude close to that. Your mechanism must be wrong, is basically how that sort of reactive prediction part goes. So this is where, again, coming back to it, having this wide range of different range of reactions allows you to look over that entire scale, and using it as this kind of a litmus test up front to predict what a potential reaction would be. Now, again, the limitations of this is we're talking pretty much about polar reactivities. This is a nucleophile electrophile or a two-electron type coupling. It doesn't really follow over for things like homolytic reaction conditions. The other one that can be done too is on a much more, without having to go right to the actual K values, you could start doing simple things colorimetrically as a simple assay. So what you could do here is start off and say, I'm going to come up with 4 different electrophiles. These are the colors of those 4 electrophiles. They're all these blue kind of dyes. And then I'm going to rank and try 3 different nucleophiles across that system. You can combine the two together, and all we're doing is saying after a fixed time point between all of them, I can quickly look at them and say what my overall assay might be in order to rank what the relative speeds might be. Now, if you look at this pairing here, these ones have already been assigned where you've got a relatively large N over here, and down here a relatively positive E value. Remember, what we're looking for is large sums of N plus E. So based on that, we'd expect that corner is going to be really, really fast compared to this corner is going to be really, really slow, because that's our lowest N and most negative E. So what they would do is in a titrometric plate, without having to run time course, you could basically set the whole thing up, dump the materials together, and take a snapshot and say, well, based on that, there's sort of my Pareto front between these ones. Indeed, that's fastest, but what you've got is this kind of an assay, a go, no go kind of view on a simple 1 minute time point. So having these as simple arrays allows people to do, again, if you're doing something like alkylation on an anti-cancer medication or something, you can use this as a way of saying how fast does this reaction actually have to be in order to potentially be a released nucleophilic warhead that then is going to be capturing some site inside a molecule or whatever. A lot of the early perturbations of things like antibody drug conjugate comes off the same idea, where you're saying I'm creating a very nucleophilic or a very electrophilic species that has to survive in some sort of a cell media, right? The last one is just the overall prediction of selectivity. So if I had a molecule like the one up at the top, this molecule has embedded in it a nucleophilic furan and, let's say, a nucleophilic alkene. Now, this is something where you have to be a bit more liberal in your values, but you could say, based on the Meyer reactivity scales, I know what a, let's say, alkyl furan might have. So I'd pull a value of, let's say, methylfuran, And then over here, I'd pull the E value from a simple alkene, depending on what your R group is. Based on whatever those two E values are, you could then say for some species, excuse me, these are both nucleophiles. But I could say that what is based on that nucleophile and this nucleophile, if I have a common electrophile that's actually competing against both of them, which one do I think is going to outcompete the other, and what's the ratio of reactivity I could potentially see? So in this case, if you, based on the Meyer scales, if the nucleophilicity of the furan was, again, 5 times that of whatever you have over here, only 1 times, then what you'd expect is if you have a common electrophile that could see both of those two groups, well, then you're expecting to see 5 times more reactivity at one center versus the other. It allows you to potentially go through and at least predict in advance and say, is it worthwhile trying to do this intermolecular competition to hit one functional group over another? The problem with it, though, is you have to make a good, just like any pKa argument, you're checking it against an overall scale and saying, based on that scale, how does this map over a known value? Because what you're doing here is you're inferring that the natively measured value of, for example, like the furan, is a real predictor of what your aggregate molecule would actually look like. Same thing for a compound like this. This is an example of taking some electrophile and saying, I'm going to run the reaction in 2 different possible solvents that might be nucleophilic. Am I worried that this nucleophilic solvent is going to compete with my substrate as far as an electrophilic type substrate? So an example of this, anybody run like an amidation type reaction at some point? So simple amidation requires you to go through, right, and have simple amidation reaction. You're going to take a carboxylic acid, you're going to take some activator, and you're going to convert it. Let's say this is like EDCI or something. You're going to be converting it to the carbodiamide type system, right? You're going to be doing a carbodiamide activation to give you a very reactive anhydride type species. One of the things you can do with this is go look up those kind of electrophiles that he's made, so these kind of anhydride or carbodiamide type coupled compounds, and look at, does a carbodiamide compound like this react at what rate with methanol versus ethanol versus propanol? And this is where some of the early coupling reactions, normally we wouldn't want to put a nucleophilic solvent like methanol together to do these amidations. Your expectation would be the solvent would actually compete with your electrophile. There's actually reactivity windows where for the certain kind of substitution over here and over here, they run just fine in methanol, but they will not run in, let's say, water or other component. And you can go through that part authentically and at least make an early prediction. Some of those ones have been used for things like what we're now doing for the synthesis of GLP-1 inhibitors. Are you guys familiar generally with this? This is changing the world in terms of what you can do. These are 30 and 40 mer amino acids. They're not the type of thing you can easily make on scale by doing peptide ligation on a resin. They all have to be made by synthetic amide coupling of long chain materials fully in solution, which means we have to go to solvents that are not just DMF and DMSO. These are semi-alcohol solutions that you have to go through and do predictions of how much might I lose by solvolysis before I do this reaction. And again, being good at this is amazing because, number one, if you can pull this off, you look like a wizard because you can look at a system and say, you're calling your shot. It's the Babe Ruth thing of saying, yes, I think this reaction will work or not. And again, if you pull it off, people will think that you're magic. But it has real consequence, right? Instead of saying, I've got this 40 or 50 mer amino acid that I have to go through and do a solvolysis study on, that is a lot of money you have to spend to get an empirical piece of data when you can look at something like this and say, don't waste your time, you're nowhere close, right? So this is a really important way of sort of focusing on what could happen. Just to link it back, the Hammett values do have a very strong embedding in this. So what they found was that these different reactivity scales can be used to figure out, first of all, the old Hammett sigma plus values are actually very, very well correlated to the Herbert Meyer's electrophilicity values. So it means that even if you didn't have the E value from some system, you could go back to the historical data from the different sigma values, and there's conversion factors that allow you to pull those over. So the different reactivity parameterization scales do have correlations because at the end of the day, these are all rate versus rate or equilibrium versus equilibrium. They're based on the same common underlying physical chemistry. So there are ways of sort of taking different data from different systems and pulling them together. So this is where I want to bring this back quickly to multilinear regression. So again, read group. There. You guys should probably take over. This is the stuff that you guys are sort of focused on a lot, and it comes back to Matt Sigmund was the one that sort of rebooted this. His philosophy was, okay, we know about linear frontage relationship. We're talking about a delta delta G, but the original formation of this was to say, all right, we remember in the original perturbation, the starting material and the product, if those are both at exactly the same energy, then we can actually extract differences in rate, which is only due to difference in the transition state. And the one system where that is absolutely always true, where the starting material and product are exactly the same energy, is enantiomeric reactions, right? This is where a case where if we start with materials that are just enantiomers in the starting material and product, it's really, this assumption is absolutely perfect. So it's a really good place to go looking for these other predictive behaviors. It's also, remember, one of the worst things you've ever had to do for people that are doing synthesis, and you've been tasked by whoever's above you to come up with an enantioselective reaction. It feels like throwing bones because you have no freaking idea when you're going to hit that, right? You're basically try another ligand, and go. This provided a visibility of saying, if your task is set a single stereocenter, and if this is the reality, you're under kinetic control of it, you actually have a way of potentially thinking in advance what you should go and try. That's why this was so important, because it actually gave a handle. The original Sigmund proposal was based on this. It's an allylation. What he's doing is saying, I am taking these conditions and I'm making a nucleophilic bromine or allyl system, and I'm making that enantiomer. And I can do the same thing on a ketone. All right, these are my catalysts that I'm using to do that one. And what he did is he worked through a series where I will study the enantiomeric ratio against different parameters. And the original one was to simply say, I can learn a lot about the allylation of one substrate and one series of catalysts. And by learning on that one, I can now figure out that, in this case, the Charton values, this is something that was an early part to describe steric bulk. Charton values of your catalysts were a really good predictor for figuring out what the enantiomeric excess would be. How he originally used this was two things. First, he was able to say that there does exist this kind of linear correlation, which is kind of like back in the linear frontage, the Hammett values. That's our rho value. So that's the degree to which a substrate, in this case, so these individual dots here correspond to different substrates. What he was able to show is that for substrates like this and this, changing your Charton value gives you a really high return on investment with your enantiomeric ratio. So that's a good thing. It means that I can say that if I were to go through and modify my catalyst, going to something with very high Charton values here is predicted to give me a pretty good jump in my enantiomeric ratio. Awesome. 2, if your real job was to work on this substrate, and you see that that is the correlation across this one, what you learn is I could try to build a substrate that has a Charton value, let's say over here, but because it has a very flat response, it's not worth my time trying to come up with a catalyst that might exist on that far right side of the scale, because I'm not really predicting to have any benefit to this one. So the first was, hey, look, there's linear energy relationships where a parameter, in this case the Charton value, can be used to tell you what your return on investment possibly could look like, and it helps you guide back and say, if I have to go design new catalysts, I at least have something to hold on to that says I need to design a catalyst not just bulky, but bulky that has a parameter like this that's helping to inform what I'm actually going to go and do. This was the first sort of jump through. The problem they ran into is that if you go to different substrates, in this case they started to go to other reactions. This is like a nucleophilic setting that you're doing an alkylation basically at this middle center here, or set by that middle center based on a distal value. The problem they ran into is single parameters. In this case, the Charton values that work so well for that allylation has no correlation when you go to this other compound. And again, initially, this is kind of where the field stopped until Sigmund picked it up. People knew that some things, sigma was a good, or it's like the parasigma values is a good predictor for some kind of properties and not for another. So what people were generally doing is running a whole series of reactions, trying a parameter. Does Charton work? No. Okay, does sigma work? No. Does sigma metal work? No. And they're just sort of doing this one-off to look for straight lines. His jump was to say, well, wait a minute, I can use a bunch of different parameters as a linear series of equations to come up with something that is additive or subtractive. So basically, it's acknowledging that for certain reactions, sigma does a pretty good job of explaining some of the phenomena, but it doesn't explain every part of it. What I can do is take sigma parameter at 50% of the sigma parameter values and maybe 40% of the Charton values and then some other fitting factor, and I can come up with an equation that's actually mixing all these different components together. This is the multilinear regression sort of phenomenon. So what we're saying is a bunch of different parameter values can be tested, where what we're trying to do is fit what coefficient goes in front of that parameter value to say, does it matter or not? So a positive value means it's part of the correlation. A negative parameter value across that means that that's anti-correlated. And all you're doing is you're running through a large series of these different values in order to come up with a predicted measured versus extrapolated. And again, it really only works so well just because what you're doing here is you're scanning through what could be infinite number of parameters for these large sort of values. But because we're dealing with an antinumeric ratio, we are by design working on a system where the starting material and the product have to have the same energy, and we're isolating this delta delta G. So it was a really, really big jump. What we're going to talk about on Monday is a couple examples based on this one, and then we'll bridge over to the thermal effects that we can do to sort of change reaction design. All right, I'll see you guys on Monday.